All right, today we're going on a bit of a bug hunt. But we're not after just any bug. We're targeting one of the sneakiest, most destructive problems in all of software, the memory leak.
You ever wonder what's really going on when your favorite app just crashes out of nowhere? Or when your whole computer starts to slow down for no good reason? Well, there's a good chance the culprit is this invisible little saboteur called a memory leak.
Okay, so before we can catch this thing, we gotta understand how it operates. What exactly is this silent bug that causes so much trouble?
Think of a program like a busy person at a library. It needs to check out books, which in this case are just chunks of computer memory, to get its job done. Now, a memory leak, that's when the program finishes with a book, but just forgets to return it. It leaves it on the table and goes to check out another one, and another, and another. You can see where this is going, right? Pretty soon, there are no books left on the shelves, the library is a mess, and everything just stops.
And this isn't just a problem for some small, obscure app. We're talking about the really critical stuff, the bedrock of our digital world, Your operating system, the web servers that run the internet, device drivers. A lot of this is written in powerful languages like C and C++. The trade-off with that power is that programmers have to manage memory by hand. They have to remember to return the books themselves. And when they forget, well, that's how you get a memory leak.
Okay, so if we know these things are a problem, why don't we just find them and fix them? Well, that's the tricky part. This brings us to what's known as the investigator's dilemma. For a long time, bug hunters have been caught in this really frustrating bind.
You've basically had two choices, and neither of them were great. On one side, you have static analysis. Think of this as the detective who casts a super wide net. They can scan the entire city in like an hour, which is awesome, right? The problem is, they flag hundreds of totally innocent people as suspicious. It's fast, but it creates a mountain of false leads. Then you have the other option, dynamic analysis. This is the detective who picks one suspect and tails them for weeks. They're going to be absolutely sure if that one person is guilty, but while they're doing that, they're missing every other crime happening in the city. So you were stuck. You had to pick speed with a ton of noise or accuracy that was painfully slow.
But what if you didn't have to choose? What if you could get the best of both worlds? Well, that's exactly what this new method is all about. It's this really clever two-stage solution that changes the game entirely.
So instead of having one overworked detective trying to do everything, this new approach is like a smart detective team. You've got two specialists. First up is the scout. Their job is to do that quick, broad scan of the whole crime scene. Then, and only then, you bring in the investigator. And their job is to do a deep dive, but only on the suspicious clues the scout has already flagged.
So let's break that down. Step 1, the scout's mission. This is our static analysis part, and it just blazes through 100% of the code. And as it goes, it uses these special little tags or annotations to mark any piece of code that looks even a little bit suspicious in how it handles memory. The key here is that it's not trying to find the final culprit. It's just creating a short, manageable list of potential suspects for the next stage.
And here's where the magic happens, the handoff. The investigator, using this really powerful technique called directed symbolic execution, takes that short list and goes to work. It doesn't waste time looking at anything else. It focuses only on those suspects and basically tries to recreate the path to the crime for each one to prove without a doubt whether it's a real bug or just a false alarm. And get this, the power of having that second step, the investigator, is just incredible. This verification stage is so good at its job that it eliminates over 80% of the initial suspects from the scout. Think about that. All that noise, all those false alarms that developers used to have to chase down, just gone.
Now, this all sounds amazing in theory, right? A perfect team. But a good detective and a good scientist needs proof, hard evidence. So the real question is, how does this new method actually perform when you put it up against the old ways of doing things?
Well, let's take a look. The researchers who developed this built a tool called MLH, which stands for Memory Leak Hunter, and they put it head-to-head against some of the big, established tools in a standardized test. And the results? They're pretty stunning. You've got established tools like the Clang Static Analyzer scoring a 0.70 on accuracy, and Infer scoring a 0.39. Not bad, but not perfect. And then you have MLH, the new method. It scored a perfect 1.00. Let that sink in. On this test suite, it found every single real bug and had 0 false alarms. A perfect score. That just doesn't happen. Okay, but a perfect score on a test is one thing, right? The real world is messy. So the real test is, does this thing actually work on real, complex software? The researchers did exactly that.
They unleashed this tool on some of the biggest, most important open-source projects out there.
And just look at this list of where it found real confirmed bugs. We're talking OpenSSL. That's the software that helps secure a huge chunk of the internet. FFmpeg, the engine behind countless video players like VLC and streaming services. Even Radar-A2, a tool used by cybersecurity pros. These aren't trivial finds. These are real-world bugs in critical software that have now been fixed, all because of this new approach.
So, let's step back for a second. What's the big picture here? Why does this matter so much? What makes this detective team approach such a potential game changer?
It really all boils down to that one brilliant idea we talked about. For so long, it was a trade-off. You could be fast or you could be accurate. You couldn't be both. This new method just shatters that trade-off. By combining that fast, broad scan with a super focused, deep verification, you finally get the best of both worlds. You get speed and you get accuracy. And that leaves us with a really exciting thought, doesn't it? This scout and investigator model works wonders for finding memory leaks. But what's next? What other really nasty, hard-to-find software bugs could we hunt down with the same idea? The case of the memory leak might be getting a whole lot easier to solve, but the hunt for truly secure and reliable software, well, that's just getting started.